Hello, and welcome back to the series on linear algebra. So, this video will be the final video on vector spaces I will be covering. And I'm going to be looking at a special case, which is functions, essentially. The next video I'll be uploading will only be optional, and it will be the proofs of a few of these different cases, because we're going to need those. So, the example I'm going to be going through is here. It's this special vector space. Now it's this notation. So it's f to the power of s. Okay, and what f is any field and s is any set. What it is f to the s it's the set of all functions that take s and map it to a field f. Okay, so it's a set of all maps from s to f. We define addition on f to the s and scalar multiplication on f to the s as follows. So when f and g are elements of f to the s and a is an element of f, then we have this linearity. Now this is a term which you'll become familiar with, okay? Linearity. You'll see this all over mathematics and linearity, and it's a feature of linear forms, bilinear forms, and tensors, and all sorts. So think of these f and g as like functions, even though they're not explicitly functions. We'll think of them, they're just members of f to the s, but they are maps. So we have this first property here. So f plus g, so you take two of these, f and g's, these maps, and these are acting on an element s, and they can be they're like distribution, okay? So they split up. So f plus g to the s is the same as f acting on s plus g acting on s. Secondly, when you have any scalar element a in the field f, a multiplied by f times s is the same as doing f on s and then multiplying it by a, okay? So an example of something like this is, say that, we'll go through it in a minute, but for instance, when you have functions, so if you have a linear map, then a function would be, say you have the first one, so we know that the first one is not true for sine functions, because sine plus cosine acting on x is not the same as having sine of x plus cosine of x. Okay, so this is where that fails, and 5. So we'll go through some more examples, but most importantly, f to the s is a vector space over f, okay, over the field f. And here are some special cases. So case 1, if we have a set which has elements 1 to n, and we identify any map which takes that set to a field f with the corresponding tuple. So it's the set f, the first element 1 goes to f of 1, the second element 2 goes to f of 2, all the way up to n, which goes to f of n. Now this can be identified with this notation, f to the n. And we've seen this before. This is the set of n tuples of elements a1 to n. So what this is like a bijective map. So if you have a map here, so one example is a permutation map. So if you have maps here, one is a permutation map. So what that is that we'll just label, it will send elements one to another element. So this could go to, for instance, 1 could go to 2, 2 could go to 3, 3 could go to 4, and n would go back to 1 again. That's one map. Another map would be 1 goes to 3, 2 goes to 4, but that would be another map. But this f to the n is a set of all maps. Okay, so essentially what it is the set of all n tuples. So all the permutations of that set. So essentially it's like a permutation group, okay, which you've seen before, or will see in the future if we haven't seen that. Secondly, our second example is like the first example. It's the set of all those tuples, but we're using this operation, and we're crossing the sets, and we define the we define the map. So we take f, we put in our set 1 to n, we cross it with our second set 1 to m, and we define it by labeling it as the following matrix. So it's the matrix with entries f1 of 1, f all up to f1 of m, down to fn of 1, to fn of m. And this is the same as before. It is a map, but now it's a two-dimensional map. Okay, and these can be identified with the set. This is the notation we're going to use. The set of matrices m, n times n, over our field f. It's the set of all n by n matrices, okay? And see these elements here, a11, a1m, they are just members from our set, okay? So we can have, it's essentially a two-dimensional permutation, okay? And we can have, so if these were natural numbers, you would have the set of all natural numbers. But in the future, we'll look at when you have a basis, and when you can find out whether that basis of matrices, or something called a basis of matrices, will, well, or a set of matrices become a basis when they are something called linear independent. And this is important. This, I'll recall this in the future, and this will be important for us. So it's a set of tools, okay? Thirdly, we have essentially the set of all the maps where we label f as, these are just some examples by the way of these. There are more vector spaces, but these are vector spaces, and we'll prove these in the next video, but that's optional. So this is the set of all maps f from the natural numbers, an indexing set which is natural numbers to f, and it's the sequence f1, f2, f3, all the way up to, well, there is no cap in the natural numbers, okay? And these are the set of all infinite sequences, okay, in our field f. And finally, I haven't finished off this last part, but in the next, let me just rub this out. So we're going to go through the next part in the next video, but that is all the examples I wanted to cover for today. So in the next video, we're going to follow off part D, and we're going to do the proofs of some of these. And in the future video, for the final part of vector spaces, I'm going to go through some questions and some kind of questions to test your knowledge of vector spaces. Before we then we'll go from vector spaces, then we'll do subspaces, then we'll do linear maps, and then we'll really get into linear algebra with matrices and dimension, kernels. Okay, so thank you for watching. See you in the next video, which will be optional. Otherwise, I'll see you in the next video after that. Bye.